It's my great honor to introduce the speaker today, Professor Nick Holonyak. Nick received all 3 degrees, bachelor, master, and PhD from the University of Illinois, this department. And in the 50s, he went to their lab. That's where he contributed to this silicon transistor technology. He invented semiconductor laser and light emitting diodes in 1962. And after that, he pioneered many fields, including quantum wave lasers, impurity-induced disordering, oxidation to lasers. And among his inventions, there is one which you use very often at home, but you probably do not know. That is the light dimmer. You know, the dimmer, the story according to Mrs. Holonyak, how he invented the dimmer, was Nick had to take hot bath instead of shower. So one day when he was relaxing in a hot tub, he was looking at the light, which was too bright, and he was thinking about a way to reduce the intensity of light. And while he was twisting his hair, he got an inspiration. Nick still has a lot of hair, so he has a lot of ideas to come. And one day he was at True Value store buying a dimmer to replace the old one at home. And he was asking the sales lady all kinds of questions about the dimmer. And this sales lady was wondering why this curious professor, he asked so many questions. She didn't know. She was talking to the inventor of the dimmer. This is like someone is holding this laser pointer in front of Nick. Yet he doesn't know. He's talking to the inventor of the laser. Okay, so let's hear the first-hand story of Nick, of transistor technology.
Good afternoon, everybody. Thanks, Shunlin. Actually, I'm going to do some stuff which is the same as what I did in September. I'm going to repeat a little bit of it, but not too much of it. And I'm going to fill in some gaps that I know I must have created in the fall in what I'm going to talk about. I'm going to talk about 2 things. If John Bardeen were alive, he'd talk to you about the early days of the transistor, particularly to a group like this. And so I'm going to do part of what John did when he talked about the early days of the transistor. Maybe I'm the last one to hear his account of the early days of the transistor. And maybe I'll add a little bit in there that John wouldn't tell you, because he was a modest man and he wouldn't reveal some things, particularly when he was pointing at himself. And then I want to go from that into silicon and how the silicon technology began. Silicon technology did not start at Silicon Valley. It started in the East Coast, not on the West Coast. So I'm going to try to cover both. That's a little bit too much for one meeting, but I'm going to try to do it anyhow. And let me see. I got too many pieces of cord here. If that's on, let me start with this first slide. In the summer of 1989, Shockley died. And John Bardeen called me up to talk about it. Then a little bit later, the IEEE had approached him to write an obit. But John didn't want to because he was out of contact with Shockley. But then the IEEE wrote it, sent it to John, and John wanted me to read it. So I took it home and then read in my old copy of Shockley's book this following statement. This book had its origin in a series of lectures given at Bell Telephone Laboratories in connection with the growth of the transistor program. It thus owes its existence basically to the invention of the transistor by John Bardeen and Waller Bratton. That's Shockley's statement. That's who he said invented the transistor. Now, when John and I were talking about this, when I brought the obit back and he wanted me to see what I thought of it, and I more or less thought that what the IEEE wrote was okay, but then that got us into an extended discussion about transistors and some odds and ends and things about transistors. And at some point, when I mentioned that there was still confusion about who invented the transistor, he says, well, then you ought to look at my copy of Shockley. And there was more than the preface. There was this statement in Shockley's handwriting to John Bardeen, who made a book like this a need, Bill Shockley. You interpret it. I have my interpretation. You interpret it yourself. And here is a picture I showed you in September. This is John in his office at about the age of 80. Wonderful person. I won't dwell on that too much. And then here's a picture of John standing right here. there was a platform in about 1965 or 67 or 68, something like that, and he's telling the folks here about the transistor, and he's holding up a vacuum tube because at this point he's smiling because, you see, tubes were very cheap and transistors were expensive in the beginning, and John had fears that the transistor would have just small use here and there for certain purposes, but would not necessarily replace the tube. Well, by this time it was obvious that the tube was on its way, it was doomed. And look at it, it's, you know, a cell phone might be smaller than that now. But you're not going to implant that in someone's chest for a heart pacemaker or a hearing aid or a cell phone or whatever. And when he came here, he came with this box. I showed you this. He showed it to us in a room around on the northwest side of the building. And this was the first time we saw a transistor in Urbana. Here's an oscillator transistor, and here's an amplifier transistor, and a keyboard, and all kinds of regular electronic components, and a little reminder here to John so he could key this thing and play little tunes. And what stunned me at the time was there was a toggle switch here which we replaced. When he flipped the switch on, the thing worked. Vacuum tubes didn't do that. So I knew, this is not the same old electronics anymore. We're looking at something different. And then if you look at the back of this, here's that oscillator transistor, and here's the regular radio componentry that existed. Everything is authentic and the same, except somewhere in some bad baggage handling, someone broke the circuit here, and I replaced this capacitor, but I left the old one there because this box is historic. There were 3 of these made in 1949. One was his, one was Walter Bratton's, and one was Bell Labs's. So that, again, points at the transistor and who made the transistor and who made it happen. Now, when Bardeen gave this talk, the early days of the transistor, he started out, this is one of his diagrams. We've modified it only slightly to enhance it a little bit. But basically, you have the primitive notion that you can take a resistive material. In this case, these were great scientists, and they knew it ought to be a semiconductor. In the 20s, Lilienfeld wouldn't have known that because he didn't know that much about semiconductors, and he didn't know that much about quantum mechanics, and he couldn't have known what Bardeen put here. But anybody could have thought of the fact you make a contact here and a contact here on a resistive piece of material that's got some kind of gunk that conducts, and put a plate up here and put a field across it, and maybe you can induce charge in here and make this thing conduct more or less as a function of the signal that you put on this plate. And what Bardeen put on here was the energy band of a semiconductor in the so-called flat band case. He's putting electrons up here, so he put the Fermi level up a little bit. And then here he indicates you put some positive charge here, you induce more negative charge here, and that puts a little bit of a well here, a trough, along the surface of conducting electrons. And here is a field effect. And they didn't know how to do this. If you evaporated some material, you made a polycrystalline film, and that wasn't a good piece of material. So John, having proven that surface states were creating great problems, he understood very well inversion layers on semiconductors, and he knew there was an inversion layer, or one could be induced on a piece of silicon. So they took a p-type piece of silicon, which has an n-type thin inversion layer here. You're not going to modulate thick material, you want to modulate thin material. And what's thin? An inversion layer is thin. And they put an insulated point contact here so that you could extract electrons out of this n-type layer and bring them up through this insulator up around here where you have this bias. And Walter Bratton and a chemist by the name of Gibney had already learned that you could change the surface states on this with an electrolyte. So they put this electrolyte on here and an electrode in the electrolyte so that they could vary the potential on the electrolyte and vary the density of electrons in here, and then vary the resistance behavior, the conductance behavior of this thin layer. Electrons would come out of the P layer along here, or along into that disk, into that spreading resistance. They'd modulate that spreading resistance, and that would be a field effect. And it worked. And you notice, I pointed this out before, he didn't call that a transistor. He called that an amplifier. It was a field effect amplifier. But it was no good in a certain sense to those of us who do electronics, because this electrolyte is slow. So they felt, okay, we'll replace that. They checked this out in germanium after they did silicon. They checked it out in germanium, and then decided they'll put, ignore this, they'll put a gold disc here on top of germanium, put a hole in it. The gold disc will sit on top the outside. Underneath it will be an inversion layer. That will be the spreading resistance. And the contact to the spreading resistance will be through this hole. John told me that Walter had an accident or something and it didn't work. But I think that as I look at this diagram in greater detail now, with the advantage of time and further knowledge, they had a grain boundary here. This was polycrystalline material. You didn't have good single crystalline material. And so you don't throw this experiment away. They moved the tungsten point from here. They moved it out to the edge, and they did their experiment. In other words, here was the gold. They took the point contact from inside of here where it should have been. They moved it to the edge, and Walter got some kind of gain, some kind of effect. Now, those of you who saw the movie Transistorized, which was about 1999, PBS, Phil Foy in the movie says something about he was in the room, and Walter said, my God, this thing's got gain. It got, and Phil was talking about this. At any rate, then they modified their experiment. Now you can see I modified Bardeen's picture. This one that he signed. You see, here's experiment A, the gold disc with the hole in it, and I indicated where the tungsten point should have been, but then Walter moved it out here, and with different bias than field effect bias, something different, he got what looked like transistor action, and so then they made experiment B. This was experiment A. Experiment B is to take this plastic wedge, wrap a gold strap around here, split the strap on the bottom, then you got two electrodes. You got one that we now call an emitter and the other one that you call the collector, and so I labeled emitter up here and collector up here. It could have been the other way around, and I indicated where the gold strap went around here. And here then is transistor number 1, 16 December 1947. And then a week later they demonstrate this to the Bell Labs so-called brass, as Bardeen called them. And here they realized that you didn't have to have two line contacts, two gold contacts, that you could go to point contacts, as point contacts were known in detector diodes for radar and all that kind of stuff. So here are 2 point contacts coming out through an insulator. Here's one, I'll call it the emitter. Here's the other one, I'll call it the collector. And the crystal itself is in this metal case, which is the base. Here you have the transistor in the form that I showed it to you in that box. And this was the so-called type A transistor, point contact transistor. Incidentally, we already have nanoelectronics. Go read the reference. Go read Torian Whitmer, crystal rectifiers, and see how they made these, how electrolytically you sharpen tungsten points and so forth. You know what? That's what atomic force microscopy and tunneling microscopy is all about. This is a nanocontact and a nanocontact. Nano is not new to us. And when Bardeen described us, to those of us 50 years ago in room 141, taking his course in semiconductors, he drew this diagram. It doesn't matter if we worry about the surface. John knew that the energy bands were tilted, and if they got tilted so that the valence band was closer to the Fermi level than the conduction band, there would be holes here. And this is N-type material, and there are electrons here. And I put this H label here, and I put this E label here. This diagram is his. And I put this line here to indicate where I could have put P over here and N over here. In other words, that point contact acts like a P-N junction. So for all intents and purposes, if the P-N junction had not been known, Bardeen would have been nevertheless still talking about a P-N junction. an artificial one in a sense, but nevertheless, P and N. And when he talked to us, holding his notebook like this, he turned around to us and he grinned a little bit and he said, if Schottky had looked here to see what the holes were doing, the transistor would have been invented. In other words, you see, Bethe, Schottky, everybody else chased electrons back and forth across this barrier, but nobody looked to see what holes were doing. I know if Bardeen had not been the guy who did that, he would have said who did it, because he never took credit away from other people. Never did I see him take credit away from other people. When I play that back through my mind, I know what John was telling us. John looked to see what the holes were doing, and the transistor was invented. Now, so then we can create this diagram, which is another one of his diagrams. Here's the germanium block, N-type. Here's my emitter point contact. Here's my collector point contact. Incidentally, when we were talking about Shockley's death and the obituary, he told me about the business of Bardeen, having created this term emitter, collector, and base. And as I told you in September, you forward bias this and inject some holes. When the holes are injected into this N-type material, since that you've got conductive N-type material, dielectric relaxation says to the electrons, move up and compensate those holes. And so electrons move in to try to compensate the holes, and holes and electrons will recombine if you give them enough time. But if you put a collector close enough, the injected minority carriers, the holes, can diffuse to the collector, be collected. So here at low impedance, you have put in current on this input, and at high impedance, you have taken out essentially that current, and ergo gain. And here comes the name then, transistor, transfer resistor. You've moved the current from the input to the output, but you've gone from low impedance to high impedance, from low resistance to high resistance, transfer resistor, transistor. And that's the origin of the name. Now, there was one ambiguity. The ambiguity was that, if I back up just a second, how do I know that I don't have a little bit of that surface channel up here? And so maybe the holes aren't traversing the bulk. Maybe what they're doing is going along the surface. And so I have to look into that. And there was a gentleman by the name of John Shive at Bell Labs, and Shive did this experiment. Shive took a wedge, not a wedge of an emitter and a collector on a plastic block, but a wedge of germanium, and he put an emitter, put a point contact on one side, a point contact on the other side. You see, if you look at the topology of this wedge is coming out at you, and if we look at it and we want surface conduction to go around this thing, or around out here and back around here, or anywhere like that, we're going to have a big path and a lot of problems in resistance. But if we go through the bulk, it's going to work fine if it works, if the bulk is really what's happening. And it worked fine. It was just like Bardeen and Bratton's device in all respects. When Shive showed the world this, not the world, but the Bell Labs, because the world, they weren't showing this to anyone yet. When Shive told this to his colleagues and described it, Shockley jumped up. This is in writing, in Bardeen's writing. Shockley jumped up because he knew that he had to tell everybody at that point this hidden work in his notebook where he had been jumping from the point contact to the junctions and working out transistor theory in his notebook. You see, up to a certain point, everyone had been cooperating and telling everybody something. But at the point when Bardeen and Bratton came across the point contact transistor, in essence, everything went up in smoke in terms of the friendliness of the place. And Shockley at that point worked and worked and worked and worked out in his notebook what turned out to be p-n junction theory. Now, that is a wonderful piece of work and very important because technologically the point contact transistor was doomed to die for technical reasons. But you've got to understand the idea, it now exists, and it came from Bardeen and Bratton and the point contact transistor. Whether the point contact transistor is going to exist or not does not matter. It produced the idea of the transistor. There was no idea of a transistor. There was an idea of field effects, but there was no transistor idea. Okay, so then finally we come to this wonderful picture of Bell Labs, which is their propaganda picture. Now, Everyone's seen this picture. Mine is not the same as the ones you see. Mine, did I show you this in September? Does anybody remember? I didn't show you this, did I? This picture has been more or less suppressed. I tried to get it published and all that, and everybody steps on it. And I don't think it's right, because it's tampering with history. It's the spring of 1980. Bardeen walks into our lab, and he asked me if I'd seen Electronics magazine. I said, no, they get it across the street, meaning over here. And so I grabbed one of the grad students. I said, don't ask any questions. Go get it, bring it back. And Bardeen and I are thumbing through it, and we come across this picture, which he knows about. He's this far away from me. The lab table is here in the journal and magazine, and he's right here. And he says, boy, does Walter hate this picture. I know Bratton personally as Walter. And I said, why, John? Isn't it flattering? You know, I'm thinking, they didn't have their jacket on or something, you know, maybe it's not flattering. And John is, you young kids have taught me this. I wouldn't have used this term before. I can see he's a little bit pissed off. Because if you ask him a question, and he doesn't think it's such a good idea, his head goes slowly like this. But in this case, he made a face at me. And then his head went like this. No. He says, that's Walter's apparatus in our experiment. And Bill, he didn't say shock me, he says, Bill didn't have anything to do with it. So I thought, gee, I can't go grab the notebook and say, John, let me write that down. He's going to turn around and walk out on me. So I said, John, please, sign the picture. He did. And I knew that that was a memory marker. If you ask me, when did this happen? It happened then. You go look in the library and see in spring of 1980, if you don't see this picture in the magazine, but you won't find his signature. But if you look at mine in the lab, the photocopy, this is all in the dots of a magazine, but this is in continuous tone. He signed that magazine when he told me the story. Little by little, it's becoming clear to me the three men were not co-equal. The transistor did not come out the way Bell Labs said. It came out more the way the movie Transistorized said it came out. Now, at this point, if you don't think much of the point contact transistor and what they did and all that, fine. In fact, I really don't care if you care or not, but I got a piece of germanium in my hand that's better than what they worked with. It's polycrystalline, but it's big grain size and everything else, and I could just offer to any one of you, whether you've been in 344 doing research and all that, and say, here, go make me a transistor, and let's see what you do. I doubt if any one of you could make one in less than a day, and I doubt if many of you will make it in less than a week, and will know how to take that piece of germanium and go make a transistor. You see, that was a brilliant thing. No matter how they got to that point, they got to a transistor without a technology, without anything that we know today about how to do all that. That was a remarkable development, and certainly worth the Nobel Prize. All right, now I switch on you. We're in big trouble, you see, because you need a technology, and you've got to have transistors. The world needs them and wants them. And there were many. It took 2 years to make a junction transistor after the point contact transistor. It took 2 years to learn enough, grow enough crystals, grow junctions, and learn how to do it. And then finally, the best thing that happened was Bob Hall in Schenectady doing experiments on PINs and purifying crystals and all that. Bob realized that he could make a PIN simpler if he just took a good piece of germanium, went into the handbook on phase diagrams, metallurgical phase diagrams. He grabbed indium off on the P side, antimony on the N side, alloyed. He stuck indium on one side thermally, antimony on the other side, and he regrew a so-called alloyed region. And here I have something like that, except I switched to silicon. I didn't make this. Some other guy made this in 1954. He had a P-type piece of silicon that you see here. It wasn't oriented perfectly. You see some tilt here and tilt here. He put gold antimony up here, heated the crystal, and the gold antimony dissolved some silicon. When he cooled the crystal, the silicon that's in the solution here in the gold then begins to grow out on the mother crystal, on the parent crystal, and it grows out N-type because of the antimony. The the acceptor doping has been diluted, the antimony doping is high in the gold, and N-type material grows out like this on the parent crystal. And the same thing happened here, and here's the collector, and here's the base, and here's the emitter. Now, you can look at this and say, this is magnificent, because you can set up and automate and do this in a wonderful way with germanium. IBM even went so far as to automate the process. They thought they could just buy a few silicon transistors as needed from a little startup in Dallas. And they never admit they made any mistakes. At any rate, you even, if you work hard enough, can close the dimension from the emitter to the base by something down to microns. But you're going to have a lot of trouble, and you're not going to like it. And you're going to have this kind of a structure. This is the one I just showed. And you see, you're going to have a hard time keeping this from plunging through and this from plunging through. You're going to make more short circuits than you're going to make good transistors. It is not a good technology to be making a transistor from both sides. But this technology worked fine from about 1950 to 1960 and put billions of transistors into the world cheap. And electrical engineers and circuits people could work on transistor circuits and learn about transistors and all that. This was very important. Hall deserves big awards for having created the process. At any rate, we have to get better than this. And we have to use silicon. And so in about 1954, it was my good fortune to go from John Bardeen's laboratory to work with this man. Do any of you recognize him? I don't mean you professors. Do you young people recognize him? No, you do, Norm. But how about the rest of you? Put up your hand if you recognize him. How many of you know the Ebers-Moll equations? This is John Moll of the Ebers-Moll equations. This is the man who probably had more to do with the existence of an integrated circuit than anybody you can name for me. If you want to debate it, we'll debate it. This man had been charged at Bell Labs with making switching devices. The Bell system switches, and they needed better switches, electronic switches, not mechanistic switches. And so I argued with him and said, well, let's do it in germanium. No, germanium's too leaky. We've got to do it in silicon. Well, the technology is only a technology for solar cells and a few things like that. We don't have a technology. He says, we'll have to make it. And the switch he wanted to make is this. Ignore these devices out here. That's a diode, a diode, a diode, a diode. Ignore those 4 diodes. But just look at this center region right here. Here's a PNP and an NPN, and they're hooked up in a funny way. In the point contact transistor, to match the collector to the load, you frequently degraded the collector a little bit. You did something called farming. You ran a pulse in there, you ran some heat in there, you screwed up the collector a little bit. And sometimes a funny thing happened. Your collector current would turn out to be, in a grounded base configuration, would be greater than your emitter current. In other words, you had a so-called alpha greater than 1. And Shockley from p-n junction theory had predicted, when they knew about this, they called that a hook collector. Shockley proposed that really was an inversion layer. In other words, it wasn't something that looked like a PNP. It was something then that looked like a PNPN. So Jim Ebers of the Ebers-Moll equations published a paper in 1952 where he shows this. He shows a PNP, the collector of the PNP driving the base of an NPN, and the collector of the NPN driving the base of the PNP. And you put a resistor here shunting this emitter, and you put a resistor here shunting this emitter. And if I put a voltage between here and here, between the plus here and the minus here, ignore this diode in the center here, what will happen is this emitter is shorted out or shunted out, this one's shunted out, so the 2 transistors aren't doing anything. But then when I get up to a voltage big enough to either break down this collector or break down this collector or break down this diode, avalanche diode in the center, because you can set the voltage better. The two transistors may differ in breakdown voltage. So you take and put a diode here that's a little bit lower in voltage in terms of breakdown than either collector. And now when we run up the voltage to the point of breakdown of this, our avalanche here, we draw some current through this resistor, and we draw some current through this resistor, this transistor turns on, this transistor turns on, and we have a feedback loop that says, do something or else we're going to violate continuity of current. And what happens is the transistors, the two collectors switch into forward bias and can rebalance the current, and you have a switch. And indeed, the circuit model showed that a PN-PN switch would switch, but there ain't any. And John Mall says, yeah, but it should work. We got good reason to believe it'll work. Let's make it. And let's make it out of silicon. So, and he had good reasons for that. And he says, okay, we'll find the technology. We'll develop the technology. Now, here's what we had. This is 1992, and this is an 85 or 90 pound silicon crystal. This is 1954 and 55, and this is a 3-ounce silicon crystal. We had silicon crystals about this size. Remind me before I'm done that I want to say something about this silicon crystal. I want to go back to it, but I don't want to tell you right now. And so we've got these crystals, and we've got the ability to saw them, dice them, etch them, and all that. Not the fancy technology that exists today, but we can do that. And we're going to make devices out of slices of this. And we're going to make them using diffusion and evaporation and alloying. We're going to do something more precise than what I showed you with the gold on the silicon. We're going to figure out something better. And there were evaporators at Bell Labs, not many of them, and here was one of them. Actually, this one was in the research area, and we were in the switching area. But you understand, we're trying to do switching devices at an early state of the art where we're doing as much research as anybody is doing in so-called research. In other words, those are artificial divisions. The real divisions are in people's minds. And at any rate, if you look into the bell jar and if we had a better figure, you'd see there's a water cooling line coming in here, cooling this bottom electrode. Then it's looping around to cool the top electrode. Then it loops around again to cool the 2 electrodes on top, 2 electrodes on bottom. The bottom one we've got set up so we can put a tungsten filament in here that we can evaporate metals from. And the top one we've got set up so that we can put a stage up there to put pieces of silicon that we want to evaporate metals on. And we're going to learn how to do that. And as John Mall gave a seminar a little bit like what I'm talking about now, 10 years ago at MIT, where he describes this technology. All I'm going to do is correct a few places where he had some problems in memory. He's older than I am, and his memory sagged a little bit before mine did. But here is a blown-up view of the top heater, and here is a blown-up view of the aluminum loop, the tungsten loop on which we put our aluminum for evaporation, or our gold. When I drew this, I should have put a box around here to indicate that this is merely a blow-up of this top piece, a different view. And I'll let you grad students sit there wondering why we made this like my bow tie. To see, we're going to heat this piece of silicon, and these are just drill holes that we've put in here because we're going to evaporate aluminum from here up to here and deposit it on that silicon. And we have a mechanistic shutter we can put here so that we can grab off the first oxidized aluminum that we want to get rid of and get to good aluminum before we let it deposit on top of the silicon. And we can deposit it on cold silicon, hot silicon, whatever. Tannenbaum was trying to do this before us and was having troubles trying to get aluminum to stick right on hot silicon, and we solved that problem on what turned out to be his machine. So he has the advantage because he owns the machinery. In other words, we can be dispossessed. And here, at Christmas 1954, here's what we already had made. This is a P-type piece of silicon. We have diffused into the top some phosphorus. That was not simple to do, and I had this in a pill box, and here was some of my writing that said what we did: 5 minutes, red phosphorus, 700, 7.5 hours, 1100 in nitrogen, drive in, 1/100 of a mil removed. Then here's my recipe for how I evaporated the aluminum. But at any rate, there's an N-type layer on top of this crystal, and then we have evaporated this P-type aluminum there, and we have made a PNP. The only trouble with our PNP was we did not have very high doping from the aluminum, and so our alpha was only 1/10. We wanted 9/10 or more. and we only got about a tenth. But we already knew we were on the road, that this would yield something. In other words, we would have to do more work on our diffusions and so forth to get this working. And we got there. Now, this is not going to be very good, but it shows you, I had squirreled away a piece of the crystal, which was the silicon PNP, and there was a cross-section on this Polaroid of that P-type crystal here, an N-type diffuse region, and then regrown from aluminum P region here, so it's a PNP. And then I had some of my notes on the back side, which I moved to the front side. I cut it and moved it so that the photographer could show what I had written on the back and what we had done in diffusion and so forth. Let's not worry about that. But the date on it is, that's my initials, that's 1955, and spring of 1955. And here's something further. When Milton Fing first saw this, he realized we had done parallel processing. When we were making one of these things, we were making a second one, we were making a third one. As soon as you saw our mask, you realized we were parallel processing. And on one piece of silicon, we were making multiple units. Now, if I invoke and jump ahead of myself and invoke the oxide, you will begin to realize we could begin to metallize across on the oxide. And that technology too came from Bell, but the person who used it first in industry was Bob Noyce. If he were alive, he would have gotten a Nobel Prize for the integrated circuit. At any rate, here we have evaporated on our N-type contact onto our N-type diffuse region. P here is the P-type of the crystal underneath, and P here is the evaporated aluminum and the thin regrown P-type region on top of the crystal, on top of the N region. So PNP made from one side, not from two sides, referenced from one side. And so we're going to ultimately defeat the hell out of the alloying process. And here's just another view of the same sort of thing, but this was color, but this thing has gotten faded. This was rephotographed about 40 years after it was done or more. I'm deliberately pointing that out to you. I got good reason for that. And then, of course, we could do other things. We made ring-based structures. They're crude because, incidentally, in another room not far from the evaporator I showed you, there were two people working on the Kodak photoresist process to lay out patterns. But that wasn't far enough along that any one of us would have delayed our work to introduce that into the processing that we were doing on silicon. You see, but the right ideas are being worked on. And here's another view, probably a different one, but the color shows you the aluminum evaporation here, the gold for the diffused layer, and the P underneath. And so in the fall of 1956, in the fall of 1955, I went in the Army. And John Mall wrote up some of what we had done, and a paper came out in the Proceedings of the IRE in September of 1956. And this diagram comes out of there. I modified it. I show the regrown region under our evaporated metals here and here and here and here. Now, Tannenbaum, whose evaporator we had used, had gotten a piece of NPN material diffused by Cal Fuller of solar cell fame, who had diffused in aluminum, and then I don't remember if it was antimony or phosphorus on top of that, and he had this NPN diffused from one side. His technician, who had learned how to evaporate with me, was supposed to make this P aluminum alloy region deep enough to pick up this base region here on this NPN transistor. The evaporation was too thin and the alloying too shallow, and so he had really a P-type regrown region here, and then NPN. So he had a PNPN switch. It was a transistor that was not made right. The contacts were not made right. It turned out to be a PNPN switch. When this thing started switching and giving strange effects, Tannenbaum came running to John Mall to figure out what's going on. And John Mall laughed and he said, "You made a PNPN switch, what I got Holonyak working on in Goldie." Here was my version. I had an N diffusion into one side of a crystal and N diffusion into the other side of a P crystal, and then my evaporated aluminum and my PNPN. And here was Goldie's version, which was a diffused junction. He took off the second diffused junction, evaporated gold on one side here, aluminum on this side, and those were the three versions. Later on, Bell Labs patented the PNPN switch in Shockley's name because of the idea of the hook. They couldn't do that now because the reduction to practice he had nothing to do with. And this one is in Shockley's patent, and this one is in Shockley's patent. But we never saw Shockley. Shockley never saw one of these devices in the beginning, but he claimed it. And the Bell management was in a hell of a warning to the administration. Watch out when you got your favorite people. Your favorite people may be not the people that you'll love in the end. And at any rate, Bell Labs had a favorite person, and it was Shockley. And if you read Bardeen's letters carefully, you'll find out that it drove Bardeen to leave. But at any rate, which turned out to be to our benefit, incidentally. This was in this paper in September, and the technology transfer was underway. Now, in John Mull's seminar at MIT, he pointed out that when Shockley left and set up his company in '55, Bell Labs did everything to help him, including to instruct John Mull to help him and answer all phone calls and help deliver the technology to him. Shockley was going to go to the West Coast, set up, and make these switches two-terminal because the telephone system was going to switch everything with these two-terminal switches. It was a false idea because of the problems with two-terminal switching. In our original paper, we published the fact that if you had the third terminal on there, you had a thyristor. We didn't say that. We said the equivalent of a thyrotron. It later got renamed thyristor. And that you could have made a fortune with. As a matter of fact, I'll indicate something about that in a minute. Well, by 1956, I'm in Japan, and Bell Labs attorneys have told me I can talk about everything, but I can't talk about the oxide. In the spring of 1955, the oxide was discovered at Bell Labs, and it was hidden for a while. And the oxide turned out to be a critical part of what is silicon technology. And these PNPs I showed you were also NPNs because we had very good control on the diffusion very early because of the business of the oxide and could do PNPs and NPNs. And I'm here describing our work to Kikuchi. Kikuchi at the time is within sight of the Diet building, and I got enough time. We're within the site of the Diet building in a laboratory where they're working on transistor technology, and it's all germanium. They don't know anything about silicon. As a matter of fact, I bootlegged a piece of silicon out of Bell Labs so one of his colleagues can do a hot electron experiment on silicon, because we're already into silicon, deep into silicon, and the Japanese are still working with germanium. This is the Kikuchi that later wound up for 15 years as Sony's research lab director. And the good CCDs were made during his time at Sony's research laboratory. The only thing I'm hiding from him is oxide. I'm not telling him about that because that's a legal matter, and I don't want to get in trouble. And here's what I was showing to Kikuchi. This is silicon. It's got an N layer diffused in it. It's got a ring base on it, and it's got a P evaporated aluminum emitter on top. And you notice I've pushed the electrodes out of the way so that we can photograph it. And this is my handwriting showing him what it is that we're doing. Now, at this time, thermal compression bonding doesn't exist. When I got out of the Army, the only thing I could tell that had happened in 2 years was thermal compression bonding had been done at Bell Labs. And of course, that was very important. Now, at the same time when this is going on, funny other things are going on. Bardeen is in Sweden getting a Nobel Prize, and to me in Japan comes this card. The lieutenant says, "Who the hell do you know in Sweden by the name of John?" And well, how am I going to explain this to the lieutenant? "Dear Nick, we have had a wonderful but strenuous time here in the past week. It has been like living in a different world. Had a dinner in the king's apartment in the palace shown in the picture. Returning soon to a more normal existence." He says existence instead of existence. John maintained that he was not a good speller because there are 2 or 3 grades that he skipped in elementary school when you learn how to spell. You know, yeah, we're all just people. And also at this time, this isn't a good focus, but I don't want to fix it up. This is in Kikuchi's laboratory. So you see, this is later, this is February of '57. and I'm here, and Kikuchi's here, and Shibuya, who did the hot electron experiment, is here, and some of Kikuchi's guys are here. Notice all these people are sitting here in overcoats. Nobody had central heating. Japan is still poor, and any of you who are Japanese who are here know what I'm talking about. Japan is poor. There's a few flowers here because it wouldn't have been right to be in a room to do this. And I'm describing switches, silicon, that kind of stuff, but I'm not talking about oxide. But technology transfer is happening. And maybe I'm the first person to do, and incidentally, 11 November 1956, why 11 November? I'm a GI. Why 11 November? Armistice Day, and we're off, and I can go with the civilians to Sony. This is Sony's research lab. This might, I didn't check with Leo Osaki. I knew Leo in Japan before anybody knew him, but I don't know if this is the lab in which he did his tunnel diode work, but at any rate, this is ordinary stuff, ordinary kind of equipment. This is a Heathkit oscilloscope. We got people always crying. They need the biggest, best machines, the biggest, best labs. No, you don't. You need a good idea. Oh, and also technology transfer went from the journals. This is why you publish. And Bob Hall advised an astute manager at GE that he could have the Thyrotron he wanted. He had to read this Bell Labs paper. And so GE picked up the version of the device that I had made, but they changed. They were better with N-type crystals, and they could do a deep gallium diffusion to make a P region here, and they made another one from the other side, and then they were very good at engineering nice thin gold layers on tungsten plates, and so with that tungsten backup plate, they could regrow an N-type region here. So from the top you have N, P, N alloy, P diffused, N grown crystal, P diffused, N, P switch. But this is big with tungsten contacts on it and everything else. This thing is too big to be Bell system switches, but it's perfect to be high voltage and high current. In other words, tens of kilowatts. So if Shockley had had the good sense to put on the third electrode, he could have been wealthy beyond belief. Don't tell me that Shockley exceeded everybody else. His biographer says that only he perceived everything and knew everything and all that. That's crazy. Bardeen never claimed that. And Shockley had no right to claim that either. He doesn't. I don't know if there's bright minds in here that exceed by far those kind of guys. You have to think it. You have to believe it. Anyhow, technology transfer was going on, and when I got in the Army, my reaction was, well, I find them doing this at GE, but they don't understand it very well. So I go back into the PMP and switch business. And here I want to show you something. Bell Labs is making an NPNPN, a 5-layer device, where the PMP and switch switches in from either direction. But one emitter is always up at high voltage at 10 volts or something like that. It's not worth a damn as a symmetrical switch. And Aldrich, my partner, and I come across something called a short emitter. Put this voltage that I got on here, plus minus, and this junction isn't doing anything. Now, when I raise the voltage high enough to get to the avalanche of this JC2 junction here, I'm going to draw some current. This is going to act as an emitter and inject some holes that will be collected here. This emitter, this region here, is shorted at this point and clamped at this potential. And at this point, the voltage is fixed at this metal potential. But where these holes come in here and then come sliding out this way conductively along this resistor here, the voltage is more positive here than it is here. Now, the voltage here of this NP is low, but the voltage here of this NP is high and injection occurs. And so this PNPN operates in that polarity. And that's obviously symmetrical, and it operates in the other polarity. When I showed this to Jim early and wouldn't tell him what it was, he sent Ian Ross to come see it. Ian Ross wound up to be the president of Bell Labs. And he doesn't tell the stories in John Mall's way. And so, to me, John Mall's a hero, and Ian Ross isn't quite a hero. But at any rate, he hinted to me someone else had come across this. Bob Noyce, working for Shockley at one time, had come across some of it. And Noyce tried to spook me that that he was going to win an interference that we had going on this. And I told him, yeah, and if you do, you won't be at Fairchild, you'll be working for Shockley. When the interference was over, he lost, we won. This is your wall dimmer, incidentally. I'm showing you this for good reason. That's an integrated device. If you go build me one of those with components, you'll need those 9 components that I showed you in the Ebers-Moll equation, circuit. You need 9 components. In other words, integration of componentry and functioning is well underway. It's just who winds up with the best lawyers in the end that wins, I guess. And so 35 years later, before they tore down our building, here's one of my handmade devices. I ran it again. You see, I go out to 30 or 40 volts, I draw some current, and then it switches on to low voltage. I go in the reverse direction, and obviously Aldrich and I had done this by hand. We put stripes this way for our diffusions and stripe the other way, so we knew we'd get overlap, but we didn't make the device perfectly symmetrical. We didn't try to do high technology. But you can come up, pull this out of my drawer, and it works. You can't go get me any nano thing anyone's talking about and go pull it out of their drawer and demonstrate it. Here I'm in old electrical engineering research laboratory, and I want to show you something. Back here is a switch, a junction box, and here are some fuses and stuff like that, and a brick wall. And this is where I did this 35 years later. And here, about that time, is our laboratory. The university has no soul. They tear apart old buildings in the name of progress, and then frequently erect what? Skata, as the Greeks say. At any rate, here was that junction box right here, and about here I was doing this work. And in this lab, Shunlin, was where the quantum wells were first done, right back over here somewhere, the oxide, the disordering and all that in this old building. And incidentally, it's not a clean room. You need clean rooms for certain purposes, but you need something else most of the time. I have lots of these pictures. I don't know if the university has them of other kinds of things you could see there, but I just wanted you to see that to let you know that there was something in that bare spot, and there's not even a tombstone there. Now, that big device I was holding, in 1960, I was still at GE, and I'd come recruiting. And I dropped that off on Bardeen, this device, which I showed you in cross-section, a different one, same thing. I dropped that off on Bardeen because when I moved to his laboratory from the tube lab in the old building, all people laughed at me. They said, gee, that's just so crystal set, you know, little points on crystals and all that. And if you really want to build amplifiers and do things that put out watts and all that and make audio amplifiers and all that, you go down to the stock room, you get tubes, transformers, resistors, capacitors, inductors, and you start building. Build your power supply and start making. They're talking about micro and milliwatts. That's no good. And, well, I got news for them. The biggest SCR now is 4 inches in diameter. And goes into the thousands of amperes, into several thousand volts, and is megawatts. And your power line is being run by these and ships and stuff like that. That's a transistor device. And I was very proud to hand that to John because that came out of the hook collector and the point contact transistor. Don't tell me the point contact transistor wasn't worth anything. There's an author on the West Coast that high-tech people dote on, a guy by the name of Gilder, and he is dumber than hell. I mean, he wrote that the point contact transistor set back transistor technology. He's nuts. There was no transistor before the point contact transistor. There was no SCR and everything else. And you see, the people who don't know are telling you the facts, and they don't know. And at the time that this happened, we were in Bardeen's office in 1990. The last time he told the story of the early days of the transistor, he told it to NHK television. And here, off of that tape, John and I are looking at the SCR and so forth. The Japanese had asked me there what I was doing there, and John explained he wanted me there because I could help him a little bit. And then here he and I are looking. That's where the control rectifier showed up. I gave it to him in 1960. He handed it back to me in 1990 to hold up as one of the things that was part of what our work was. And then finally here, I want to show you about 1980. Here's Kikuchi again. Now Kikuchi is not in the electrotechnical laboratory at this point. He's Sony's research laboratory director. And when the hierarchy wonders where the Sony money came from for a Bardeen chair, it's mainly due to this guy. Bardeen had met him first in 1953. Little did I know I'd be in the Army there in 56 and would be introduced to the highest scientific establishment. And Kikuchi was teaching these young guys about semiconductors, and then later wound up as one of the captains of the semiconductor industry as the research director at Sony. And here he's visiting us, and we have just had lunch together, and the photographer got us out in front of the Union Building, about 1980. Now I want to conclude with this. Excuse me for running over a little bit, but I got to tell you this. This was in the cover of Science magazine in December. And this was called the Breakthrough of the Year, Nanocircuits, and this is carbon nanotubes. Look at the fanciful thing that someone has put together here. Like a power station, like a chemical engineering station. You see, look at these like pipes and stuff. What small creature put this hybrid structure together? Well, Bob Noyce, if he were alive, would tell you the reason that they did a lot of the metallization and the integrating was to get away from the tyranny of a single transistor and splicing these things into circuits one at a time and so forth. In other words, the integrated circuit let you put in lots of active elements with lots of circuitry simultaneously. Where is my breakthrough on the circuitry in this? I don't care if this thing switches. Is it a good switch? And if I hand you a bunch of this stuff, incidentally, when I worked for John Mall, someone in Bell Labs comes in with a polyethylene bag of silicon needles. You can make silicon needles. What if I hand you silicon needles and say, go make me something the equivalent of an Intel chip? Try it. You will shudder at how great the technology is that led to crystals, including now huge crystals, and a processing technology that shrinks, and gets density, and gets your wiring and your device and everything simultaneously. These are experiments. This isn't a technology. And whatever possessed these people to do this, I almost wrote them a letter, and I almost said, cancel my membership in your society. Anyhow, beware. The young minds are sitting on the breakthroughs. What we're hearing as breakthroughs right now aren't breakthroughs. This isn't a breakthrough of any kind. And no one in the integrated circuitry business is living in fear of this. And incidentally, I throw it out as a challenge to anybody that wants to debate this on this stuff, including U of I people who think that they can put these things down one at a time with a mechanistic procedure. A mechanistic procedure won't do it. You've got to think of something better. Thank you.
When John Moore gave a talk at MIT about 10 years ago, he created the Nick's board, which was used in Silicon Valley later. And actually, MIT invited Nick right away to give a talk there. But Nick turned it down because he could not go. And actually, so he returned the talk 10 years later at UIUC. So we are lucky to be here to listen to his talk. So let's take a couple of questions.
Nick, what happened to that tiny silicon you're talking about?
That little piece?
1955.
Rossi, one of our former grad students, was running a big silicon operation at Monsanto turned MEMC. And I gave him these. I had several of them. And see, these came to me accidentally because when I got drafted in the Army, the fellows I worked with took all the stuff in my desk and threw it in a box and sent it to my parents' place. So I didn't steal these out of Bell Labs. But when I got out of the Army and didn't return to Bell Labs, I didn't send them all that stuff either. And so those were Bell Labs crystals. And Rossi said he was going to hang on to them. I wanted him to examine a defect situation in those crystals vis-a-vis modern crystals. And, you know, business is business. One thing leads to another, and I don't know what he did with them. But fortunately, he made me the pictures. And Ben Streetman used the pictures in his book, but now he's got other pictures. And there's history in that little crystal there. There were several of those that I had. I kept them for a long, long time in my junk. Rossi should have them. But I don't know what they're worth. They're worth something to history, artifacts. Incidentally, one thing I didn't say. Those transistor pictures that I had are devices that were in the desk too. And you can come, I don't know where they got mixed up when we moved from one lab to the other lab, but you can go take data on our devices that we made in 54, 55. Nobody is handing me this new work and saying, here, you can take data on our device. I can hand you LEDs you can take data on. I can hand you lasers you can take data on. I can hand you transistors over 40-year periods or more that you can take data on. I don't see anything like that happening that anyone's spooking me about with these one-at-a-time switches that are made out of molecules.
You mentioned that John Mall encouraged you to work on silicon. Who was really fundamental in switching from germanium to silicon?
Jim Early was working on germanium. Ian Ross's people were working on germanium. Mort Prince was working on silicon diffused rectifiers. Some people in and around Jerry Pearson, who Norm knows well, and Cal Fuller and so forth were doing diffusions because of what happened on the solar cell. And Carl Frosch is the man that was also helping us with diffusions and came across the oxide. But when Ray Warner up at Minnesota writes about the early stuff, he went out with hepatitis. He wasn't working on silicon. And he was working with germanium and stuff like that. Ian wasn't working on silicon. They all inherited that and all came in later. The switch work was ahead of the transistor work, so they broke apart John Mall's group and said that some of us had to go help get the switching transistors further along and transistors in general. And so then Bill Hittinger was given a group. I was in his group later and so forth. But the best work was, of course, under John Mall. John Mall was a tremendous mind and thinker, and I consider the Swedes as having insulted him. Silicon went from John Mall directly to Shockley, directly to the people who were set up Fairchild and Intel did not know anything about silicon. They got it from Shockley, who got it from Bell Labs, who got it directly from John Mall's group. The prime architect of silicon being made into transistors and switches and all that was John Mall. Pure and simple.